A major American volcano overlooking a city of 700,000 people has a 1 in 1/5 chance of unleashing a catastrophic event in the next 30 years. Not an earth-shattering eruption, not a sky-blackening ash cloud, but a silent, fast-moving flood of geologic debris. The United States Geological Survey has given this specific threat the highest near-term probability of any volcano in the Cascade Range. The mountain is Mount Hood, the indigenous Wy'east, and its most immediate danger is not fire, but water, and mud, and rock. Over 3,000 acres of glacial ice are perched near its summit, a frozen reservoir of potential energy. But the trigger for this disaster may not be what anyone expects. The new data shows it isn't rising magma that poses the most urgent threat. It's what's happening in the cracks. But here's the detail that tells the real story. On October 19, 1805, the explorers Meriwether Lewis and William Clark were navigating the lower Columbia River, their journey nearing its end. As they approached the mouth of a tributary flowing from the south, they encountered a bizarre obstacle. The river was choked with an immense volume of gray sand and sediment, so thick that the channel was barely navigable. It was unlike anything they had seen on their entire expedition. Clark famously noted it in his journal, naming it the Quicksand River. What the explorers did not know, what they could not have known, is that they were not witnessing a normal process of erosion. They were documenting the immediate, still unsettled aftermath of a major volcanic event. They were paddling through the fresh deposits of a massive lahar, a volcanic mudflow that had scoured its way down from the slopes of Mount Hood just a decade prior. And the strangest part of this story is not that a volcano can produce a river of sand. It's that today, entire communities, highways, and homes are built directly on top of the very same deposits documented by Lewis and Clark, in a valley that is still named after their initial warning, the Sandy River. To understand what is happening now, you have to understand the mountain's restlessness, a subtle but persistent activity that rarely makes the news. In the last 2 years, the volcano has been trembling. Between December 8th and 13th of 2023, a minor swarm of quiet earthquakes rattled beneath the summit. In June of 2021, a more significant swarm struck, culminating in a magnitude 3.9 quake felt by some residents. On March 1st of that same year, dozens of smaller quakes occurred over just 45 minutes. The immediate assumption, the one everyone makes, is that these swarms signal the ascent of magma, the prelude to an eruption. But the scientists at the David A. Johnston Cascades Volcano Observatory in Vancouver, Washington, say that is not what their instruments are detecting. The reality is something stranger, and in some ways, more unsettling. The official USGS statement on the 2021 swarms reads, "What we are seeing is slip on a fault or faults." It is easiest to achieve such earthquakes if you push a little water in there and jack the fault apart just enough to induce slip. The mountain is being jacked apart by its own water. The heat from the magma chamber, which sits miles below the surface, is superheating groundwater trapped within the volcano's edifice. This pressurized, intensely hot water is being forced into a network of pre-existing cracks and faults. It acts as a lubricant, reducing friction, and as a hydraulic wedge, physically prying the rock apart. The earthquake swarms are the sound of the mountain's bones cracking under this immense hydrothermal pressure. Every tremor is a tiny report on a process of internal fracturing. Weston Thelen, a research seismologist at the observatory, spends his days listening to these subterranean conversations. The story they tell is not of an imminent magmatic blast, but of a mountain becoming progressively weaker and less stable from within. It's a fascinating, if slightly terrifying concept, a volcano being literally pried open by superheated steam. Curious what you all think about that idea. The quiet power of water, not fire, being the agent of change. Now, here is the part nobody is putting on the news. This hydraulic jacking is only half of the story. There is a second, even quieter process at work on Mount Hood. Near the summit, just below the peak, lies a feature known as crater rock. This is not the remnant of an ancient crater, but a relatively new dacite lava dome, extruded during the volcano's last major eruptive period in the late 1700s. Clustered around this dome are several active fumarole fields, the most vigorous of which is named Devil's Kitchen. There are no apostrophes in the official name. It is a raw, primordial place where the volcano breathes. Hot, acidic gases, rich in sulfur, vent from cracks in the rock. Surface temperatures here simmer around 192 degrees Fahrenheit, but subsurface measurements indicate the gases are leaving a much hotter environment, one exceeding 572 degrees. These gases are not just venting, they are chemically attacking the mountain itself. The sulfurous compounds mix with groundwater to create a form of sulfuric acid. This potent acid is dissolving the strong, solid andesite and dacite rock, the very bones of the volcano, and altering it into soft, weak, slippery clay minerals. This process is called hydrothermal alteration. It is, in essence, a form of chemical rotting. The mountain is digesting itself from the inside out. The result is that large portions of the upper mountain, particularly around the unstable crater rock dome, are losing their structural integrity. Solid, interlocking rock is being transformed into a material with the consistency of slick, wet clay. This reality creates a terrifying possibility, one completely independent of an eruption. A sufficiently large section of this chemically rotted, internally fractured edifice could simply fail under the pull of gravity. It could collapse in a massive landslide, a spontaneous sector collapse, with no new magma required, no warning from rising earthquake swarms, just the inexorable physics of weak material on a steep slope. And this brings us back to the ice. Perched on these very same weakened flanks are Mount Hood's 12 named glaciers. A sudden, massive landslide of hot, altered rock would act like a skillet dropped onto a block of ice. The heat transfer would be instantaneous and catastrophic, flash melting enormous quantities of glacial ice and snowpack. This sudden deluge of meltwater would mix with the collapsing debris, the clay, the rock, the soil to form the one thing volcanologists fear most at Mount Hood, a lahar. This is the part the headlines do not capture. A lahar is not a flood of water. It is not brown water carrying sticks. It is a completely different physical phenomenon. David L. George, a research mathematician at the Cascades Volcano Observatory, co-developed an advanced software model called DCLAW, specifically to understand and predict the behavior of these flows. As he explains it, a lahar behaves like a fluid, but it is a dense, powerful mixture of solids and water. Think of wet concrete, but moving at highway speeds. These flows can be tens of meters deep, with the consistency of a thick slurry, but the momentum of a freight train. They carry everything they rip from the landscape: soil, ash, ice, and boulders the size of houses. They do not flow around obstacles. They flow over them or destroy them. The largest trees in the Mount Hood National Forest would be snapped like twigs and incorporated into the flow, becoming battering rams. This torrent of geologic cement would not follow the gentle curves of a river. It would seek the path of steepest descent, scouring valleys clean, jumping riverbanks, and burying everything in its path under a thick layer of material that, once it stops moving, sets into a substance as hard as stone. This is what poured down the Sandy River Valley just before Lewis and Clark arrived. This is the one in 1-5 threat. The odds of a lahar in the next 30 years on the Sandy or White River valleys are calculated by the USGS to be between 3.3% and 6.7%. People buy lottery tickets with far worse odds. This is a known, statistically defined risk hanging over the landscape. We go deep into the science behind these events on this channel. If you appreciate this level of detail, subscribing to catch future deep dives is probably a good move. To understand the scale of this threat, we have to look back in time, into the deep history written in the mountain's own flanks. The geology reveals that Mount Hood doesn't erupt continuously. It operates in distinct episodes separated by centuries of quiet. The most recent major phase was the Old Maid eruptive period, which geologists Kenneth A. Cameron and Patrick T. Pringle have precisely dated using dendrochronology, the study of tree rings. Sometime around 1781, the volcano roared back to life after a period of dormancy. It began by slowly extruding the thick, pasty dacite lava that would eventually build the massive crater rock dome we see today. As this dome grew, it became unstable. Parts of it repeatedly collapsed, generating superheated rock avalanches called pyroclastic flows. These flows cascaded down the southern and western flanks, instantly melting the Zigzag and Reed glaciers. The result was a series of enormous lahars that surged down the Sandy and White River drainages. These weren't minor events. They were landscape-altering torrents that buried entire mature cedar forests, some trees hundreds of years old, under many feet of rock and mud. It is the buried, subfossil remains of these very trees that Cameron and Pringle studied to pinpoint the eruption's timeline to between 1781 and 1793. The AAA flow that defines the Old Maid Flat, that vast, barren-looking expanse in the Sandy River Valley, is the deposit from this period. When Lewis and Clark documented their quicksand river in 1805, they were walking on ground that was less than a generation old, created by a volcanic event whose climax had ended just a dozen years before their arrival. Their meticulously kept journals became an unintentional geological survey, a snapshot of a river system still attempting to recover from a volcanic cataclysm. Before the Old Maid period, there was the zigzag eruptive period, about 500 to 600 years ago. Before that, about 1,500 years ago, was the Timberline eruptive period, the most voluminous and violent eruptive phase in Mount Hood's recent history. The Timberline events produced pyroclastic flows and enormous lahars that were so large they traveled all the way down the Sandy River, reached the Columbia River, and partially dammed it. The geological record is unambiguous. Mount Hood is a cyclical volcano, and the Old Maid period was not an end, but simply the most recent chapter. The 200-plus years of quiet since are just an interval. The cycle will begin again. Zoom out. And the geography makes the modern risk terrifyingly clear. The volcano sits just 50 miles, or 80 kilometers, east-southeast of downtown Portland. The valleys that radiate from its base are not empty wilderness. They are pathways for recreation and commerce, and they are places where people live. Communities like Government Camp, Welch's, and Zigzag are built directly on top of the lahar deposits from past eruptive periods. The very ground beneath their foundations is evidence of what the volcano can and will do again. According to a detailed report from Oregon's Department of Geology and Mineral Industries, known as DOGAMI, roughly 5,000 people live directly inside the mapped 500-year volcano hazard zone. These are the residents most at risk from a direct lahar impact. But the danger doesn't stop there. The systemic risks ripple outward, affecting a much larger population. The entire Sandy River Basin, which includes suburbs of the Portland metropolitan area, is home to up to 200,000 Oregonians whose lives would be profoundly disrupted. A major lahar would destroy every bridge it encounters, severing critical transportation arteries like US Route 26, the primary highway connecting Portland to the mountains. Power lines, fiber optic cables, and gas pipelines that cross the Sandy River Valley would be obliterated. But the most critical piece of infrastructure at risk is Portland's own water supply. The city's primary source of drinking water is the Bull Run watershed, located on the western flank of the Mount Hood National Forest. While it is somewhat shielded from direct lahar impact, it is highly vulnerable to ashfall. A significant eruption, even one that doesn't produce catastrophic lahars, could blanket the watershed and its reservoirs in a thick layer of volcanic ash, contaminating the water supply for hundreds of thousands of people for weeks or months. This is a vulnerability that emergency managers take very seriously. Then there is the strange irony of Timberline Lodge. The iconic hotel whose exterior was made famous by the film The Shining was completed in 1938. It sits at an elevation of 6,000 feet on the south side of the mountain, welcoming millions of visitors a year for skiing and sightseeing. It is a masterpiece of rustic architecture, a National Historic Landmark. It is also built directly on top of prehistoric pyroclastic flow deposits from the Timberline eruptive period. Guests who ski the Palmer Snowfield in the summer are, in reality, skiing on a permanent glacier that sits precariously atop an unstable, chemically rotting volcanic dome. The very thing that makes the mountain a world-class recreational paradise. Its steep slopes, its immense glaciers, its dramatic topography, is the very same combination of factors that makes it so hazardous. I think if you're finding this useful, it's worth sharing. Low-key send this to a friend who lives in the Pacific Northwest. Anyway, back to the hidden crater. One of the most persistent misconceptions about Mount Hood is what an eruption would actually look like, conditioned by the 1980 eruption of Mount St. Helens. Many people imagine a massive lateral blast or a towering Plinian column of ash that darkens the sky for hundreds of miles. While Mount Hood is capable of producing significant ash, its dominant style is fundamentally different and arguably more insidious. Mount Hood is what volcanologists call a dome-building volcano. Instead of exploding violently, it tends to slowly and quietly ooze thick, viscous dacite magma, like cold honey or toothpaste being squeezed from a tube. This magma is too thick to flow far, so it piles up over the vent, forming a steep-sided, unstable mound, a lava dome. Crater Rock is a perfect example of such a dome, a plug that has filled and obscured the mountain's true summit crater. The danger arises not during the dome's slow growth, but when it inevitably fails. These domes are inherently unstable. Oversteepened slopes, internal pressure from trapped gas, or even a simple earthquake can trigger a collapse. When a chunk of a hot lava dome breaks off, it disintegrates into a pyroclastic flow, that superheated avalanche of rock, ash, and gas moving at hundreds of miles per hour. This is the mechanism that triggers the glacier melting that leads to lahars. The eruption itself can be small and localized to the summit, but the cascading consequences, the flow and the lahar, are what travel far and cause widespread destruction. The threat isn't a single telegenic explosion. It's a chain reaction set off by a quiet collapse high on the mountain, perhaps in the middle of the night, with the resulting lahar moving silently downriver until it is too late. The challenge for scientists and emergency managers is immense. The USGS and the Pacific Northwest Seismic Network maintain a network of 8 seismometers on and around Mount Hood, along with GPS stations to detect ground deformation and gas monitoring equipment to sniff the volcano's breath for chemical changes. This network provides a constant stream of data back to the Cascades Volcano Observatory. But the quiet nature of Mount Hood's primary threats makes prediction difficult. The onset of a dome-building eruption may be preceded by clear seismic signals, but a spontaneous landslide of the hydrothermally altered rock at Devil's Kitchen might not be. A lahar warning system is in place, using acoustic flow monitors, essentially microphones that listen for the deep, low-frequency rumble of an approaching debris flow. But these systems can only provide minutes of warning. For communities like Welch's and Zigzag, located just a few miles downstream, that might not be enough time for a full evacuation. This is why the USGS, in publications like Open File Report 9789, authored by scientists like William E. Scott and Cynthia A. Gardner, emphasizes not just monitoring, but geological mapping and public education. The hazard maps they produce are not theoretical exercises. They are blueprints for survival, showing the areas most likely to be inundated, based on the irrefutable evidence of where lahars have gone before. The work of David R. Sherrod, whose extensive geological mapping has been fundamental to understanding the volcano's history, shows that the drainages on the east side of the mountain, like the White River Valley, are just as vulnerable as the Sandy. The old-made lahars flowed down both sides of the mountain simultaneously. And the largest modeled lahar event, a truly catastrophic collapse of the summit, could release an almost unfathomable 500 million cubic meters of material. While the probability of such a maximum scale event in any given 30-year period is low, less than 1 in 3,000, it remains a statistical possibility that defines the worst-case scenario. It is this combination of high probability, medium-sized events, and low probability, cataclysmic events that makes Mount Hood a very high-threat volcano in the National Volcanic Early Warning System. It isn't just about the likelihood of an eruption, but the immense vulnerability of the people and infrastructure that lie in its shadow. So what happens now? The scientific consensus is not a question of if Mount Hood will enter a new eruptive period, but when. The 200-year lull since the Old Maid period is a perfectly normal interval of repose in the life of a Cascade volcano. The hydrothermal jacking and chemical rotting are ongoing processes, steadily preparing the mountain for its next phase of activity, whether that phase is eruptive or not. Emergency management agencies for Clackamas County and Hood River County work with the state of Oregon to refine evacuation plans and public warning systems. But the apathetic nature of a threat that moves on a geologic timescale is the greatest challenge. A warning issued in 1997 about a 30-year probability feels distant, abstract. But we are now more than 2/3 of the way through that 30-year window. The clock is ticking. 3 questions hang over the peak tonight. How long can the chemically weakened rock of the summit hold itself together under the increasing pressure of its own heated groundwater? If the cycle of eruptive periods is closing in again after 200 years, are the current hydrothermal swarms the first tremors of that reawakening? And what does it mean for a city of nearly 700,000 people to live with a statistical time bomb ticking just 50 miles away? A threat that looks less like a volcano and more like a river of concrete waiting to be released. Most people who watch this far often forget to subscribe. Just a quiet reminder if you found this valuable. Deep beneath crater rock, acidic water continues its slow work, converting solid geology into future disaster. The faults are lubricated, the glaciers are waiting. And somewhere in the mountain's plumbing, pressure is building, moving at less than a centimeter a year in the dark, preparing to reclaim the valleys that were carved by its ancestors.